Hello, and welcome to our final project presentation for CS6365 Enterprise Computing. We are excited to present our Steam Game Recommender project. This comprehensive overview and demo will walk you through our project, our accomplishments, challenges, and potential future work. For a general overview, we sought to develop a Steam Game Recommender system to help users discover new games based on their history and preferences. To accomplish this, we utilize front-end and back-end technologies to address the limitations in Steam's present content discovery systems in order to enhance user experience and recommendation accuracy.
So for the data collection part, we initially were just going to use a series of data sets we found on Kaggle. But once we merged all these data sets, there were so many holes in them that we just decided it would be easier to just generate our own. And thankfully, Steam's API made this pretty easy, since they had a function to get the game details of a user, which is what was most important for us, and that got all the games that a user owned as well as their playtime, assuming that these details were public. So our application only works on players that have their profile public and their game details public. And then we also can use the API to return the friends list of users, assuming that's public. And using that, we were able to create a DFS network where essentially we'd start on a user, get all their game data, and then traverse their friends list in depth first search and get the game data of all those users. That made it really simple. It took a while, but we managed to get somewhere around 1.3 million data points through this. We also then used Steam's API to get the game details of every game that was scraped in this data set. And that would include things like the publisher, developer, the date when it was published, the user score. I didn't end up using all of these, and part of that was because of GitHub's limits of how large a data set could be. So we probably should have kept more. Those are some limitations. We could add this added later in future, but for now, all the filters that will be seen in the demo later are ones that we scraped from these details. We also used how long to beat data set that we did get off Kaggle, as well as utilized an unofficial how long to beat API to get the how long to beat times for games which were missing from that Kaggle dataset. There were a lot of holes in this, but for those missing ones, we just used the median time of all the how long to beat times, which of course introduced some bias, which we'll talk about a little bit later. But that's how I managed the data.
As for technologies used, we utilize JavaScript for the front end using the React framework due to its wide use and compatibility across browsers and devices.
For the back end, we used Python. Pandas was really useful for all the data manipulation. The surprise library was very useful for collaborative filtering. This one allowed us to easily implement collaborative filtering functions, as well as create and fit models such as SVD, k-nearest neighbor, and co-clustering. The dataset, we did use off Kaggle, how long to beat dataset, and then we also augmented that using the API, and then we used Steam APIs, as mentioned earlier, to generate the rest of the dataset. We were going to use a server hosted somewhere to host our application, but the memory usage was just so high because, especially when we were generating the pandas dataset with all the data that we gathered, it just uses a lot of system RAM, so we weren't able to fit that there. So we just used a local Flask server, which worked fine. We also used Conda to make it really easy for a user to set up the correct environment to run our application. To align with industry standards, we just used React for our front end because it's so common nowadays. We tried to optimize our system to be fast, since our competition, which would essentially just be Steam's recommendation system, is nearly instantaneous, very fast. We were not even close to hitting that mark, but I'll explain why in the future. And of course, like I mentioned, we use Conda. So for our system performance, we use implicit ratings because we didn't have explicit ratings, and explicit ratings would just be a user actually saying if they liked a game or did not like a game. We didn't have that data, so instead we calculated it as the playtime divided by the how long to beat time, and then we capped that at 2. So if a user had twice or more as much playtime as the how long to beat time, that's a perfect 10. And we decided to do the 2 times instead of, like, say 1 times, because the average rating was really, really high in the data set when we just had 1 time, so as much playtime as how long to beat time being a 10. That made the ratings really, really high, and that just made the rankings not as easy to do because there were so many ties. so that's why we ended up using 2 times. There were data limitations, as mentioned earlier, and bias, because there were so many missing how long to beat times. Most of them were there, but there were definitely a lot of holes, especially in smaller games, and especially in those smaller games, even if they weren't missing, they'd only have a few users that were inputting how long it took them to beat that game to the how long to beat website, and that would mean that there'd be very high variance and probably not that accurate timing. So there's a lot of bias introduced there, and the system would highly rank probably games that should be lower ranked just based off of that bias. And we also use some algorithmic models for accuracy. Co-clustering kind of seemed to work the best when we were testing, so that's the default. A user can select whichever model they want, and we would encourage a user to try a few and just see what seems to give them the best results at first glance, and then use that in the future. There were some challenges. Of course, we weren't able to host this on any remote server due to previously mentioned memory usage. There were some project planning things that changed. Like, for example, we were initially going to use more data sets and not generate ours, but there were just so many holes. We just ended up making our own. That's just some adaptability. And the calculation speed, it ended up taking a long time. It depends heavily on system resources. So on my desktop, which has a pretty nice processor, it takes about a minute. And on Cody's, who has running on a laptop, it takes more like 5, somewhere around there, which is very slow, especially for something like this. But the problem is that when a user submits their user ID to the system, we need to use Steam API to actually add all their game details and their playtime to our dataset, so that way we can tell how they rated those. And then we also need to fill in any missing how long to beat times using the how long to beat API, which can also take some time. And the longest time comes from jittering the test set, which would be all the games that are in the data sets that the user does not personally own. That takes some time. And then, of course, getting the ratings for every single one of those games also takes some time. So it ends up taking a pretty significant amount of time. So we tried to make this as best we could, but that's just how it ended up being. And I will demo here.
Here you can see the front-end web application for our Steam Game Recommender. We include some simplified instructions where the user can select a model to generate the recommendations. As we previously mentioned, co-clustering is the default, as it is most effective in our findings. And then they can paste their public Steam ID into this input and press submit in order for the backend to generate their recommendations. This loading bar, unfortunately, does not demonstrate the actual level of progress, but it does show that the backend is at work. And during this time, the next button is disabled so that they cannot transfer to the next screen. We have skipped some of the loading for the sake of time, so now we can view our recommendations. As you can see, this is the full list of video game recommendations, the top 99 based on our implicit ratings, as we discussed. Here we can sort by things such as the rank that they're rated, the title, alphabetical order, as well as the price, so that you can view lowest to most expensive, or the length for shortest to longest. You can also do this in descending order, so that you can view the longest games to the shortest, or the most expensive to the cheapest, if that's what you'd like. And then you can also filter the games based on certain features like full controller support or Steam achievements and things like that. This does not filter within the top 100 games, but actually returns the top 100 games that satisfy these filters, so that the user always has 99 games to choose from. You can also filter based on multiplayer types like online co-op or shared screen PvP and things like that. And then as for price and length, we have implemented a slider so that the user can view games within a range of prices, such as $23 to $50, or by length, such as games that are over 100 hours or under 100 hours. And at any time, these filters can be easily cleared to return the user to the original list. And so that is our demo.
Future work. So for future work, we have identified several potential enhancements for our Steam recommender system. These include incorporating user reviews and ratings, implementing advanced recommendation algorithms, integrating real-time data and feedback loops, hosting the backend system on a more remote server, and improving the user interface. By exploring these avenues, we aim to continuously refine our recommendation system, ensuring that it remains relevant, accurate, and engaging for users in the ever-evolving enterprise computing industry. Conclusion. In conclusion, our team has made significant strides in developing a robust Steam game recommender system. We have tackled challenges in data gathering, cloud computing, and algorithmic limitations while learning and applying these new skills in software development and data analysis. We remain committed to enhancing the performance and accuracy of our system and are excited to continue exploring future improvements to deliver a truly exceptional user experience. Thank you all for your time and attention. We appreciate your interest in our project.